Okay, when you have a polynomial over a polynomial, the first thing you ask yourself is the numerator less degree than the denominator? And it is. Check. Next, can you factor the denominator? And factor it as much as you possibly can. So I factor the denominator, I get x times x squared plus 4, and then go, darn it, I can't factor anymore. I'm going to have to deal with this. So, do you know how you are going to prepare and set up for fraction decomposition? You have a linear factor and you have a quadratic factor for your denominator. X squared plus 4 cannot be factored in the real number system. So as you break those up, know that they have to have lesser degree polynomials above them. For the linear function, that means just a constant. For the quadratic function, that means a linear, an entire bx plus c. And by the way, if your addition order is opposite what I have, and you have the x squared plus 4 first and then the x, it does not matter. A, B, and C are your A, B, and C, but you will come up with the same numerators, no matter who's A, B, and C. So once you reach this point, just like before, you're going to multiply by the common denominator. So as I distribute over this addition, I have a times the x squared plus 4. And then make sure you put a parentheses around that bx plus c times x. Now, once we reached this point, we chose some good x's to plug in. We chose x's that were zeros of linear factors. We only have one linear factor. So let's at least do what we can. What do we want to plug into x that will easily find us something? 0. When I plug in x equals 0, on the left side I get just 4. On the right side I get 4 times a plus 0. So I've got my a. Now, if we continue using this technique, then I need to choose 2 other x values to find 2 more unknowns. If I do that, at best, I'm going to create a system of 2 equations with 2 unknowns, which, preferably we'd rather not. So, do you remember that I told you something last Friday? Do you remember what I told you last Friday? If you know 2 polynomials are equal, so we've got polynomial with a coefficients, polynomial with b coefficients. If 2 polynomials are equal, the only way they are equal is if their corresponding coefficients are equal. Now I want you to see that changes one equation, if it's a 3rd degree polynomial, that is. For a 3rd degree polynomial, you get 4 equations from 1. Does that sound like you might not have to do systems of equations? Well, we will see. So what I'm going to do is I'm going to take that we already know a, and I'm going to write that in. And now let's rewrite what we have. we have 2x squared minus x plus 4 equals 1 times x squared plus 4. Let's do a distribute multiplication over addition. And now 2x squared minus x plus 4 is equal to something times x squared plus something times x plus something that has no x. So look at your right side. How many x squareds do I have on the right side? I have 1 plus b. How many x's do I have on the right side? I have c x's. And then what about a constant? And take a good look at how beautiful this is. Now I have 2 equals 1 plus b. Negative 1 equals c. And thank goodness 4 equals 4. Whew! That was a disaster possibility. So if 2 equals 1 plus b, then b must equal 1. And just flat out, negative 1 is equal to c. We've got our a, b, and c. And now we're going to go back and put all of this information in. Let me remember that was a is 1. So I'm now going to integrate 1 over x, and then bx plus c is 1x minus 1. So this integrand is the same exact function as the integrand I had in there before. It's just rearranged. Look at that cute little 1 over x. Aww. What's its integral? Now, we are about to do something we haven't done before. We are going to split the numerator. So what I'm meaning is we are now going to look at the integral of x over x squared plus 4 plus the integral of negative 1 over x squared plus 4. We just keep learning new things that we can do with our little integration puzzles. Now, take a look at this integral. And when you see how to do it, you'll see why I did split the numerator. Take a good look at it. Why was splitting the numerator so helpful? Oh dear. We're back to I blame Common Core for your algebra. Oh wait, I said that out loud on tape. I will tell you that it used to be that this was never, ever, ever, ever an issue, except for every once in a while I had someone who wasn't really ready to take calculus who did not make this mistake. Now it's just about everyone makes this mistake. So am I upset about it? I'm controlling myself from running out the hallways and screaming. Okay. Sorry, I'm over emotional. Okay. Addition in the denominator cannot be split up. The numerator can be split up. I don't know how far back I need to go to help you see that. Let's see. If I have 2 plus 3 over 7, can I split that numerator? And that means exactly the same thing. But if I have, what happens when I split that denominator? Yeah, it's an issue of order of operations. Order of operations, there is an understanding that the fraction bar says parentheses around the numerator and around the denominator. That means you cannot touch that addition in those parentheses without using a distributive property. When I look at this one, when I divide by 7, that is the same thing as multiplying by 1/7. So I can change that fraction to 1/7 times 2 plus 3. And then I can separately multiply using my distributive property of multiplication over addition. But in this situation, I do not have the ability to say division is multiplication of a reciprocal. So it comes down to spending enough time with algebra to have already sorted through these issues. And I see too many people who don't recognize that difference. And I'm going to continue to try to tell people that this is an issue. Someday, maybe they will listen. Okay, so here we are. We can do use substitution for this one. And if you think about the fact that we can do that use substitution, do you see why I split the numerator? If I hadn't done that, I would have had to do a trig substitution using this entire x minus 1. But by splitting the numerator, my trig substitution has less to work with. I have to do trig substitution on that last one. But I want to get out of there things that I don't have to go that far with, because trig substitution is going to be harder unless you can break it down a bit more. So, use substitution. Make the denominator the u. And then my x dx is replaced with a 1/2 du. And then x squared plus 4 replaced with a u. and then natural log of absolute u. I don't actually need the absolute value here, but because it's x squared plus 4. And now trig substitution. And this is actually not too bad. Now, trig substitution, a lot of the time it has a square root in it. But sometimes you don't have a square root. If you don't have a square root involved, your options are, hey, I might be able to do fraction decomposition, but we've already fraction decompositioned this thing to as little as possible. And now we run into our only option is through trig substitution to complete this. So we want to fraction decompose as much as possible, but we may in the end still have to turn to trig sub for a last bit. So here we go. What trig function do I want to use? I have an addition of a variable squared x and a number squared 2. Which trig function do I want to use? Then what is the derivative of tangent? And if you want, you can directly substitute in everything, or you can use your triangle to help you out a bit, but I'm gonna put it straight up in. My x is being squared, so that means that I'm going to have 4 tan squared theta, and then plus 4. My dx is replaced with 2 times secant squared theta d theta. And let me see, I just want to kind of make sure that you see that's x squared. Now, do you recognize 4 tangent squared plus 4? Four tangent squared plus 4 is 4 times tangent squared plus 1, otherwise known as secant squared. You can see this with your triangle as well. One way or another, you'll wind up here. And do you see some beautiful math happening? What is the answer to the integral? And then go back to the original substitution. What is theta? Inverse tangent of x over 2. I'm going to bring it back over here. And drop down that previous one, and we are done. Now this should look familiar. I now want to point out to you that the integral of 1 over x squared plus 4, I'm going to pull it to the side. Does it look very, very similar to something we have actually done before? It's been a while. Do you remember what this integral is? Yep. That integrand is the answer to the derivative of inverse tangent, arctan. That was one of the formulas you were supposed to memorize. Emphasis on supposed to. Now, you no longer need to. Once you know how to do trig substitution, there are some formulas you don't have to memorize. We want to memorize as little as possible and be able to create as much math as we can from less. When you start getting into higher level math where you have to do proofs, you begin with as little as possible. In geometry, we call them postulates. In algebra, they are called axioms. And those beginning principles are very, 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 very simple and basic. They have to be the most obvious thing you could imagine because we don't prove them. We build from them. You'd be surprised what we actually don't assume, that we actually prove things that are very obvious because we have to create math from as few facts as possible. Because anything that we put in as an understood truth without proof could be our downfall. So math is about memorize less, create more. Now at this point, I'm going to go back over to your study guide because I want to show you that in the integration formulas, wait, what happened there? Why did you move? Okay, let me see if it will let me lasso it. There we go. These integration formulas here, that's all you need to memorize. That's not as many as we had before, because this is taking out the need for those 1 over x squared plus 1 and the sort. So if you run across those old integrals that we used to have memorized, you no longer get to have them memorized. You can come up with them. Is that nice? Let's see where we are at. I'm going to stop the recording.